we are going to finish up chapter 19 and start chapter 20. So I went kind of fast through chapter 19. I will slow down when we get to chapter 20 because that's new material. All right? So we left off last time talking about preparation of carboxylic acids. So we can do it by oxidation, so that would be from chapter 12. We can oxidation of aldehydes with chromium reagents. We can also do oxidative cleavage using ozonolysis. That was also in chapter 12. And then in chapter 18, we talked about the fact that you can oxidize alkyl groups bonded to aromatic rings. So you'll recognize, if you had me last quarter, you'll recognize this slide from notes last quarter. Alkyl group bonded benzene ring can be oxidized to carboxylic acid. The commonly used reagents are potassium permanganate, sodium dichromate. The one that I use is potassium permanganate. And that is KMnO4 and base, so sodium hydroxide. And heat. All right, so here's some examples here. It doesn't really matter how long the chain is. The oxidizing, this is a very powerful oxidizing agent. It's going to oxidate it all the way down to a carboxylic acid. So all of these starting materials give the same product. You could have a chain that was 100 carbons long. It would still give you the same product. What you do need for this reaction to work is a benzylic hydrogen. So here's a benzylic hydrogen here. Here's a benzylic hydrogen here. Here's a benzylic hydrogen here. Must have benzylic hydrogen. If you don't have a benzylic hydrogen, there is no reaction. So this one here, as you can see, this carbon has no benzylic hydrogen. Therefore, there is no reaction. So here's in our little box on the test, we would write no reaction. Okay? No reaction if you don't have any benzylic hydrogen. So the NR for no reaction. All right, so potassium permanganate, we saw this in, this is chapter 18. We also saw potassium permanganate in chapter 12, doing something completely different. And that is doing dihydroxylation. Just to point out that this is low temperature here. So the temperature is kept low so that we don't have things like this previous reaction happening. Okay, so we keep the temperature low for dihydroxylation. When we're doing the above reaction, we will use heat for that. And the last thing we want to talk about in this chapter is sulfonic acids. Sulfonic acids are very similar to carboxylic acids. So you saw sulfonic acids last quarter in dehydration reactions, right? Okay, so we use this for dehydration. We abbreviated this TSOH, toluene sulfonic acid. Now that you've had chapter 18, now that name makes sense to you. Okay, so that was used for dehydration. Used instead of concentrated H2SO4. For dehydration. And I'm off the edge of the paper, so dehydration. And that, of course, is chapter, what is that, chapter 9? Chapter 9. So everything you've ever learned all year comes back in 51C. All right, so these guys are actually similar properties to carboxylic acids, but much, much, much more acidic. So carboxylic acids have pKa's of about 5. These have pKa's around -7. And the reason that they're so acidic is their conjugate bases are very, very highly resonance stabilized. So when you remove this acidic hydrogen, With the carboxylic acid, you can delocalize the electrons onto 2 oxygens. With sulfonic acid, you can delocalize the electrons onto 3 oxygens. So here's oxygen number 1, oxygen number 2, oxygen number 3. So more highly delocalized electrons. So highly resonance stabilized. Because their conjugate bases are such weak bases, they make great leaving groups. And so we saw in chapter 9 that we can use tosylates as a leaving group. This one here is ethyl tosylate. So I'm sure you recognize the name ethyl tosylate. You might have forgotten what a tosylate looks like, and that's the danger of using abbreviations. When you're doing reactions, you forget what they actually look like. So if we were going to abbreviate this, we would write CH3CH2O tos. So that's our tosylate. And we know that they make great leaving groups. So what this reaction would look like, we attack carbon, backside attack, kick off tosylate as a leaving group. That gives us ethyl nitrile. And our leaving group, of course, is the same one we have drawn above. Very highly resonance stabilized. The negative charge delocalized onto 3 oxygens. Great leaving group. All right, remember how to make tosylates? Well, let's use our retrosynthetic arrow. How do we make this? We can make this from ethanol and tosyl chloride pyridine. So hopefully that's ringing bells here for you. So although all the reactions we've ever learned come back in 51C, I try to remind you of them as we go. I remind you of them in lecture, I remind you of them in discussion, and I remind you of you on test too, I suppose. Okay, so, but what you're going to start to see is that a lot of the reagents, there's a certain few that we use over and over again, and I call them famous reagents, and there's definitely some ones in 51B that you will use a lot more than others. All right, questions, anybody? Let's start chapter 20. So who needs handouts that hasn't picked up the notes already? Nobody. You probably got a big stack in the back there. Okay. All right. All right, so here's where we start really getting into the nitty-gritty of carbonyl chemistry. So in this chapter here, we're going to talk about carbonyl chemistry with all of the carbonyl compounds and organometallic reagents. So irreversible carbonyl addition. And then in chapter 21, we talk about reversible additions of aldehydes and ketones. And then in chapter 22, we talk about reversible additions to carboxylic acids, esters, amides, and all of that. So, but this is a very general chapter. This is a chapter that you certainly do not want to get behind in, because you'll be lost very quickly here. All right, so what do we know about carbonyl compounds? It's an extremely important functional group in organic chemistry and in biology, too. It plays an important role in many biological processes. So here's a carbonyl group. This is a carbonyl group. And what do we know about structure? Well, structure-wise, we know that we have sp2 oxygen and sp2 carbon. Let's draw out the structure. I'm going to kind of lay this on its side. perpendicular to your page. So we have our pi bond here. So these are our two unhybridized p orbitals. So that's a p orbital, that's a p orbital. And those two orbitals overlap to make our pi bond. So our pi bond overlap of two p orbitals. And then our sigma bond is, the carbon-oxygen sigma bond is right here. Overlap of what type of orbitals? sp2 and sp2. So now we're going all the way back to chapter 1. So we're gonna hit all those chapters. And so then we also have lone pairs on oxygen. Let's draw on the lone pairs. What type of orbitals are the lone pairs on oxygen in? Anybody? Oxygen's sp2 hybridized, so these must be in sp2 orbitals, right? sp2. So when we hybridize one s and two p's, we get 3 sp2 orbitals. One of those sp2s overlaps with carbon to make a sigma bond, and the other two hold the lone pairs. And then we have an unhybridized p orbital, which makes the pi bond. Okay? Questions? I know it's been a while since we've done that. Substituents attached to carbonyl strongly affect the reactivity of carbonyl compounds. There's going to be, I'm going to divide these into two different types. I'm going to divide them into type 1 and type 2, and the two types have different reactivity. Type 1, the acyl group. So remember the acyl group. So this right here, that's the acyl group. So an acyl group is the carbonyl with an R group attached. When we're just talking about the carbonyl, it's the carbonyl. When we're talking about the R group attached in addition to the carbonyl, that's the acyl group. So acyl group is attached to a group that does not have lone pairs and cannot act as a leaving group. So here we have, so the acyl group is attached to a hydrogen, or the acyl group is attached to another R group. So this would be an aldehyde, and this would be a ketone. And these are both type 1, so if we compare R and H, the things that they have in common is that they have no lone pair. They have no lone pairs, and they can't be a leaving group. How do we know if something's a good leaving group or not? Remember that from chapter 7? What's a good leaving group? Weak base, okay? So it can't be a good leaving group, so these must be strong bases. So let's look. If R left, it would be R minus, which would have a pKa of, for the conjugate acid. That's how we're going to judge basicity. pKa of the conjugate acid is RH. RH is our conjugate acid, and it has a pKa equals 50. Horrible, horrible leaving group. Not going to happen. Let's look at H minus as a leaving group. Because if those groups left, that would be our leaving group, H minus. pKa, conjugate acid. Conjugate acid is H2, and that has a pKa of 36. So also a horrible leaving group. Okay, so just to remind us, again, let's label this. Good leaving groups are weak bases. These are not weak bases. Good leaving groups are weak bases. All right, so that's type 1, aldehydes and ketones. We're going to talk about them together, and that's going to be the subject of chapter 21. We're also going to talk about those in this chapter. And then type 2, acyl group is attached to a group L. So I use L. L stands for lone pair, and L stands for leaving group. So L, leaving group. and L lone pair. So any carbonyl compound that has that is bonded to a group L that has a lone pair or can be a leaving group is going to be type 2, and they're going to have different chemistry than type 1. So here, so again, this is our acyl group here. Acyl group, and it's either a good leaving group or it can be protonated to make it a good leaving group. So that's what these all have in common. So here's the examples here. If it's a chloride, it's an acid chloride. If it's an amine, then it would be an amide. OR would be an ester, OH, carboxylic acid, and if it's bonded to another carboxy group, then that would be an anhydride. So a lot of people have forgotten anhydride. I noticed that in my lab class, so that would be an anhydride, so something that we're going to be talking about this quarter. Questions so far, the two types? All right, so let's talk about what type 1 and type 2 carbonyls have in common and what they don't have in common. And I'll start with a simple ketone. So here we have a ketone. This is acetone. And we know that we can draw a resonance structure for acetone, where we break the pi bond and we move it onto the more electronegative atom. So it would look like this. This is not a great resonance structure. It's not a super contributor, but it does actually contribute a small amount to the hybrid. And so if you look at the polarization of a carbonyl group, we have partial positive charge on the carbon, partial negative charge on the oxygen. And so what all of the type 1 and type 2 carbonyl compounds have in common is that that we have the carbonyl carbon is electrophilic. So it's quite electrophilic. It's more electrophilic because we have, not only do we have resonance contributors, we also have the difference in electronegativity. And those things add together to make that bond more polar than a typical carbon-oxygen bond. And so since it's electrophilic, what we're going to see, this is the type of reactivity that we're going to see for these guys, is nucleophiles attacking the carbonyl carbon. So this is what it will look like. Nucleophile attacks the carbonyl carbon, and then we kick electrons up onto oxygen. That's the reactivity that we're going to see for all of the carbonyl compounds. This is an addition. So that's the reactivity that we're going to see. And what we're going to do is things like adding a proton source to protonate that oxygen. We'll see that coming up to make alcohols. So we have a new synthesis of alcohols. Type 2 carbonyl compounds, on the other hand, are a little bit different. Following addition, elimination occurs. So it's going to be two steps now for these guys. All right, so the nucleophile is going to attack, same as it did with the type 1 carbonyl compounds. That's going to attack. Except now we got to add an L here, so go ahead and add that L. And I'm just going to put a little lone pair on L to show that that's a lone pair and a potential leaving group. So kick electrons up onto oxygen, we get negatively charged oxygen, and then we have this group L that can be a leaving group. So that step right there is addition. Same as above. But because we have a group L that can be a leaving group, what's going to happen is the leaving group is going to leave. So electrons on oxygen are going to come down and kick off the leaving group. That second step is called an elimination. So if you look at what we have after that elimination, we've basically replaced a nucleophile with L. So it looks like it's a substitution reaction, but it's not an SN1 and it's not an SN2 because it undergoes an addition elimination reaction. So it's a completely different reaction. This is the overall. Let's summarize let's look at the overall process here. We're taking a leaving group and replacing it with a nucleophile. So substitution, but not an SN1, not an SN2. We're going to call this an acyl substitution. So nucleophilic acyl, whoops, sorry about that. Nucleophilic acyl substitution. Let me give you an example that we're going to be talking about in this chapter here. This reagent here is aluminum reagent related to lithium aluminum hydride, which you're already familiar with. Slightly different though, but in the same family. And it's a hydride source. We have negatively charged aluminum. So if you remember from, what chapter was that? Was that the, that was chapter 12, right? When we talked about lithium aluminum hydride. And so we're going to use the same arrow pushing. Arrow is going to come from the aluminum hydrogen bond. We're going to attack the carbonyl. We're going to kick electrons up onto oxygen. You're probably going to hear me say that. Attack the carbonyl carbon, kick electrons up onto oxygen. You're probably going to hear me say that like 100, 200 times by the time we get through carbonyl chemistry. So it's just so common, that reactivity. This is addition. And then let's draw the addition product. And then as you can see, we've got chloride ion, could be a possible leaving group, and that's exactly what's going to happen. So we have the negatively charged oxygen. We've got the chlorine here. We've got the hydrogen. Our leaving group is not going to be hydride. Our leaving group is going to be chloride. And so the electrons on oxygen are going to come down and kick off the leaving group chloride ion. That's elimination. Addition, elimination. And when we do this reaction, we've turned our acid chloride into an aldehyde. So that's a reaction that we're going to be talking about in this chapter. And so here's the big difference. Type 2 carbonyl compounds have a leaving group. So what we do is when we do the attack, we get something that we call a tetrahedral intermediate. Why do we call that a tetrahedral intermediate? If you see, we start off when we're sp2 carbon, and then here we're sp3. So our intermediate has changed hybridization. It's now sp3, and so it's tetrahedral carbon. So we call this a tetrahedral carbon. And the tetrahedral intermediate has a leaving group. And if the tetrahedral intermediate has the leaving group is going to leave. So we're going to be able to make predictions about what carbonyl compounds are going to do just by looking at the groups that are attached. Questions so far? Anybody? Now, depending on who you had last quarter, this reaction, this addition elimination is going to look very familiar to you. We've already seen it, this type of substitution via addition elimination twice in chapter 9, way back to the beginning of 51B. Here's the first time. alcohol, thionyl chloride attacks thionyl chloride. We attack the sulfur. We kick electrons up onto oxygen. That's addition. And as you can see, now we can label that as a tetrahedral intermediate. Really not tetrahedral because we got extra electrons here, but a negatively charged oxygen. And a second chlorine here. And then in the next step, the electrons on oxygen came down and kicked off the leaving group, chloride. So your book does this mechanism a little bit differently. Most of the professors here do follow this addition elimination mechanism for thionyl chloride. So again, it depends on who you had for 51A. Throw that positive charge on oxygen. So everybody remember that from chapter 9? And so what we're going to see is, and that's kind of why I made a point of emphasizing this reaction, is because I knew that this was going to be important for carbonyl chemistry. So that's what that looks like after that kicks off chloride. That's the first time we saw it in chapter 9. The second time we saw it in chapter 9 was for doing a tosylate, making a tosylate. So alcohol, plus tosyl chloride. So hopefully this is all coming streaming back to you right now. All right, so in the book, they did straight, they had the electrons come from oxygen and kick off the chloride in one step. It doesn't happen in one step, it's an addition elimination. So the electrons on oxygen come and attack the sulfur. We kick electrons up onto oxygen. That's addition. And then after addition, because the sulfur has a chloride which can act as a leaving group, it's going to do just like carbonyls do. So we have negatively charged oxygen. What else do we have? We have a chloride here. We have toluene ring attached here. And we have a second oxygen. So a lot of groups around around sulfur. And then we had the electrons on oxygen come down and kick off our leaving group, chloride ion. All right, so that second step, of course, is elimination. So let's label that. I need to label this up here, go back and label this up here. Elimination, and what do we get? Overall substitution. So same idea here. So atoms that are not sp3 hybridized undergo substitution via addition elimination. Okay, so that's the take-home point here. All right, so we've already seen this before. It's a little simpler actually with carbonyl compounds. Type 1 compounds, on the other hand, do not contain a group that's either a good leaving group or may convert it into a good leaving group by protonation, so only addition can occur. So here's an example of a reaction that we'll be talking about in this chapter of what happens when you take, and this you'll recognize, lithium aluminum hydride from chapter 12. And we saw that this can attack epoxides and open them up. It can also attack carbonyls. So let's draw an aldehyde. Very rapid reaction with aldehydes. Arrow comes from the aluminum hydrogen bond. Attacks the electrophilic carbon. We kick electrons up onto oxygen, just like that. And that, of course, is addition, which I'll just abbreviate with add. And we get a tetrahedral intermediate. Why is it a tetrahedral intermediate? Same thing as before. This is sp2. And after we do the addition, it's now sp3, so therefore tetrahedral. So in this case, the tetrahedral intermediate has no leaving group. R minus can't leave because it's too strong of a base. H minus can't leave because it's too strong of a base. So it's stuck with addition. There is no elimination. And so what we normally do with these guys is we add a proton source in the second step. Now, your book kind of uses different proton sources. Sometimes they use water, sometimes they use hydronium ion. I don't want you to worry about that. Okay, so in truth, when you do this reaction, if you're actually doing this reaction, this is a very exothermic reaction with water, so you cool your reaction down in an ice bath, you add a drop of water, you wait for the exothermic reaction to subside, you add water first, and then you put everything in a SEP funnel, and you shake it up with a little acid. So I'm going to let you, so I'm saying proton source in the second step, and I'm going to pretty much, well, H2O or H3O plus is fine with me for exam, so you could use either one. In other words, I'm choosing not to make a big deal about this, whether you use water or hydronium ion. And so you can see we get a completely different product here. We get an addition product, not a substitution product. All right, so type 2 carbonyl compounds do acyl substitution. Type 1 carbonyl compounds do additions. All right, questions so far? Anybody? All right. So that's there. So a little bit different there, but all the carbonyl compounds are electrophilic. What else do they have in common? Type 1 and type 2 carbonyl compounds are weakly basic at the carbonyl oxygen and are protonated by strong acids. So let's draw that. And I'll choose an ester here. So if we add a strong acid to an ester, the carbonyl oxygen, which is this one that's part of the double bond, that's the carbonyl oxygen, is weakly basic. But if you put a strong acid in there, it will be protonated by the strong acid. This is what the conjugate base would look like, a protonated ester. And this protonated ester is resonance stabilized. So let's draw some resonance structures for it. We can move electrons. We can break this pi bond and move electrons onto oxygen to relieve that positive charge. We can do that. That, of course, is not going to be a major resonance structure because if we do that, we leave carbon without an octet. So we've got a carbocation there. But we also have another resonance structure where these electrons on oxygen here can come kick in and help stabilize that. In this case, it's the conjugate acid. It can help stabilize the conjugate acid. So that is a resonance stabilized conjugate acid. Yes?
Why don't the farm resonance structures happen together? Why is there
An intermediate.
why don't what's the one break and then the other doesn't all form at the same time?
It can. I'm just showing you the 3 possible resonance structures for that protonated. Yeah. So resonance stabilized, conjugate acid. Now, you might have thought to yourself, well, why would we protonate on that carbon, on that oxygen? Why do we protonate here? Why don't we protonate here, right? We've got 2 possible oxygens. Can we ever protonate here instead of here? So let's look at that. That's on the next page. Turns out that you only get protonation at the carbonyl oxygen. When you do protonate the carbonyl oxygen, you greatly enhance the electrophilicity of the carbonyl compound. Okay, so that's a big deal. And so acid catalysis is often used to enhance the electrophilicity of the carbon so that it's more easily attacked by weak nucleophiles. So where we're going to see this is in chapter 21 and chapter 22. We're not going to really see acid catalyzed reactions in this chapter, in chapter 20. But again, I want to go back to the point of why does protonation occur at the carbonyl oxygen, not the carboxylate oxygen. Let's draw the product if you protonate. Let's compare the 2. We have this, which we drew on the previous page, protonation on the carbonyl carbon. And we can compare that with protonation at the other oxygen. And probably if I sent around, had you do a little pre-quiz on this, most people would protonate, I'm sorry why I'm just drawing the same thing again. Most people would protonate the other oxygen. So let's see why that doesn't happen. Okay, looks reasonable, right? All right, we've already shown, and so here's why. We've already shown that this one has a resonance stabilized conjugate acid. We get 3 resonance structures for this. This one here is not resonance stabilized. So if you're thinking to yourself, well, yeah, of course that's resonance stabilized. I can just do this. I'm going to write that. I'm going to do this in purple, what you don't want to do. I can just go like this, right? Can't I do that? And let's see why you can't do that. So let's draw the product of that, where you're thinking, okay, now that I can draw this resonance structure, and then tell me what's wrong with this resonance structure. What's the charge on oxygen? 2+. And I don't know, however you had for 51A, in my class I said never draw any resonance structures that have a 2+ or 2- charge. Okay, so that's oxygen. You've never seen oxygen with 4 bonds, and that's for a good reason. Okay, so you don't want to try this. So let's cross that out. All right, and the other thing is that we also know that the carbonyl is electron withdrawing. So you remember from chapter 18 that carbonyl compounds bonded directly to the aromatic ring were electron withdrawing groups, and so it turns out that also the inductive effect of the carbonyl is destabilizing. And we're used to seeing inductive effect being stabilizing. Inductive effect can be destabilizing. So if you look right here, if this is an electron withdrawing group pulling electron density away, this oxygen's positively charged, right? It's going to make it more positive. It's pulling more electron density away. And so when you have a positive charge, inductive effect is destabilizing. So that's what's going on here with this one. We have electrons pulling towards the carbonyl like that, which is going to make that less stable. Okay, so for all of those reasons, we see protonation on the carbonyl oxygen, not the other oxygen. All right, so that's going to really come back. So you want to review this when we start chapter 21 and 22. So that's really going to come back in chapter 21 and 22. The other thing is that the other reactivity for carbonyls, both type 1 and type 2 carbonyl compounds, are acidic. The hydrogen atoms on the alpha carbon of some type 1 and type 2 carbonyl compounds are acidic. Deprotonation gives rise to resonance stabilized enolates. So let me give you an example here. And I'm going to emphasize the word some. You can't do this with all of them, but some of them, type 1 and type 2. So this is what we're talking about here. So when we get to that, when we get to the nomenclature podcast, you'll see this, that carbon that's adjacent to a carbonyl is an alpha carbon. So let's label that. This is an alpha carbon right there, adjacent to the carbonyl. Base can come in, remove that alpha hydrogen. Not used to seeing hydrogens being removed from carbon too much, except when we have a terminal alkyne, right? So that might look a little unusual to you. This is not super acidic, but has a pKa of about 20. And if we remove that acidic hydrogen, we form a resonance stabilized enolate ion. So now here we can delocalize electrons onto oxygen. So this is closely related to the enol that we talked about back in 51B. Remember in the alkynes chapter, we talked about enol and keto tautomerization, all right? So this is really similar, except now we have a deprotonated version, okay? But so what we call this is a resonance stabilized enolate ion. Good news is that we're not going to really talk about this until chapter 23. So this is the topic of chapter 23 and 24. So the good news is this chapter, we're going to come back to these. This chapter, we're basically going to talk about how carbonyl compounds are electrophilic and the types of products that you get when you take carbonyl compounds and react them with very strong nucleophiles. All right, but first things first, we need to, we want to be able to predict reactivity. And so we have all these different types of carbonyl compounds, and what we want to know is which is more reactive, which is less reactive, and be able to explain why. So acid chlorides and anhydrides are more electrophilic than aldehydes and ketones. And carboxylic acids, esters, and amides are less reactive than aldehydes and ketones. And between ketones and aldehydes are more reactive than ketones. So you definitely need to know this order of reactivity, but I also want you to understand why it is and be able to explain it if you're asked to do that. All right, so we want to be able to explain that because I know you guys don't want to just memorize that, right? Wouldn't you rather understand it? There's only so much room in your brain for memorization. So at some point you have to, if you understand it, then you don't have to memorize it, and that gives you more room for other classes where you have to do more memorization. Okay, so that's sort of the idea here. All right, so in the last 3 minutes, we'll talk about this and see if we can explain this. All right. Relative reactivities depend on the relative stability of each acyl derivative. The stability is dependent on two factors, the inductive effects and resonance effects. Okay, so we're going to talk about both of those. It's a combination of the two. So let's see. Let's talk about type 2 right now. So groups where we have an L bonded to the carbonyl, L bonded to the acyl group. And so as L becomes more electronegative, what's going to happen? And what we're basically doing here is we're going to look at how the charge on that carbonyl carbon is changing as we make changes in L. So what happens, so L, if we're talking about inductive effect, as L becomes more electronegative, what's that going to do to the carbonyl carbon? It's going to make it more reactive or less reactive? It already has a partial positive charge. It's going to make it more positive. It's going to pull more electron density away from the carbonyl. So L pulls electron density away from the carbonyl carbon. This makes carbon more positive. And therefore less stable. If carbon is more positive, then nucleophiles are going to be more likely to attack it, right? If it's more positive, it's more electron deficient, that makes it less stable. It's going to be more reactive. And so more partial positive charge on the carbonyl carbon means more electrophilic. So more partial positive charge on the carbonyl carbon equals more electrophilic. And more electrophilic is more reactive. So that's inductive effect. So inductive effect is destabilizing. What about resonance effects? So let's see what happens. And we'll come back to aldehydes and ketones, but let's see what happens when we talk about how L can donate that lone pair that it has. So once again, we're still looking at the partial positive. Partial negative. So what happens as L feeds in electron density, pushes it up onto oxygen? Is that stabilizing or destabilizing? We're actually adding electron density to that carbonyl, aren't we? So resonance effect adds electron density. To the carbonyl carbon. This makes carbon less positive. And therefore, more stable. So less partial positive charge on carbonyl carbon. Equals less electrophilic. So we have two factors that are working in opposite directions, and so what that means is we're going to have to weigh these two factors to see which is more important to be able to explain reactivity, and we'll do that next time.